Hi, good afternoon, and I will share with you chapter 26. And just here, let me just have more like zoom in. Here we will analyze what is called direct current circuits, where the current is going to stay the same in magnitude and direction. Now, I will say first, there is one approach when we have one loop, and here we are going to analyze circuits with multiple resistors in series and parallel. And here just the condition is just we're going to have one loop. It's going to be easy for us to analyze. Now, we are going to also do use another method, and this is when we have multiple I will say loops, and we're gonna apply Kirchhoff's laws, and we're gonna see how we're gonna apply it and how to use the rules. We are going to talk about devices that they are really used for measuring in electrical circuits, like ammeters, voltmeters, ohmmeters, and potentiometers to measure all the physical quantity that we were talking about. How to analyze circuits that include both a resistor and capacitor, and finally how electric power is distributed in the home. Here you can see that this is like a very complicated circuit, and here we might have so many resistors that they are really connected in like different methods of connecting, and we gonna see like how really the current is gonna be different and how we can calculate all these currents. We will analyze a little bit like complex networks that they have resistors, batteries, and also capacitors. Our principal concern in this chapter is with direct current DC circuits, where they have the current is going to stay the same in the same magnitude and direction. Examples on these are really flashlight and automobile wiring systems, and the other method for connecting it is called when we use alternating current, is going to be that the current is going to oscillate between two values, or like more values is going to change, and it's going to change its direction, and this is going to be the topic that we're going to study next. The same principles for analyzing networks apply to both kinds of circuits, and we conclude this chapter with a look at how we wire appliances in home. Now, resistors in series, they are going to be connected one after the other, so the only thing that you need to think of here is what is really the constant quantity that's going to be the same, and that is actually the current. Therefore, I will say the voltage is going to be distributed based on the values of the resistors, and since V, it is I times R total, or R equivalent, and V1 is IR1 and V2 is IR2, we're going to find that R can drop from the whole, and we're going to say R equivalent is R1 plus R2 plus R3. Now, when we have resistors in parallel, they're going to be having the same voltage, and therefore I will say the current is going to divide into I1, I2, I3, and then I will say the total current is going to be I1 plus I2 plus I3, and also we can conclude that 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3. Now, of course, as I said, when you connect to the same source two incandescent lamps or light bulbs, they are going to be a little bit fainter. If you look at in here, they're gonna draw less power and glow less when they are really connected in parallel. Most of the time we don't have just series or just parallel. We're gonna have a combination of both, and therefore I will say we need to calculate what is really the total resistance of the circuit. Here I have R2 and R3 are really in parallel, and then 1 over R23 equals 1 over R2 plus 1 over R3, and then the resulting from these two is going to be added to R1, and this is how we're going to find what is really the R equivalent. Here also resistors can be connected in combination of series and parallel. Here you can see that R2 and R3 are in series, and therefore their equivalent resistance is going to be R23, and then that one is going to be in parallel with R1. Then in order to calculate the equivalent, I will say 1 over R equivalent equals 1 over R1 plus 1 over R2, 3. Now here is my first example, okay, where I have a circuit here shown in the figure, and we're going to assume that the meters are idealized, which means the voltmeter is going to have a very high resistance, and the ammeter is going to have a very low resistance. And the reading here of the ammeter is 1.25. You can see that this is measuring the current through the 25. What does the voltmeter read? What is the EMF of the battery? Now the first thing, they did not ask about it, but just I want to show you that in order for me to calculate the equivalent, I will say 1 over R 25, 15, and this should be 25 because this is 25, this is 15, and these two are in series, then they're gonna add up to 25. Then it's gonna be equal to 1 over R25 plus 1 over R15 plus 1 over R25, and then you are going to find 1 over the values and then add them, and then finally you are going to do, when you add, you're gonna take 1 over R of this value, and then this is gonna be your equivalent. Now we can calculate the voltage across this resistor because we know the value of the resistor and we know the current is 1.25. Then using Ohm's law, we will be able to say 1.25 times 25 equals 31.25 volts. We can also calculate the current across 15, because remember, when the voltage here, what voltage is here is going to be the same as voltage here, okay, and therefore I need to find first what is really the current by dividing the voltage over the 15, and this is going to be 2.08. I will say now resistors 15 and 10, they add up to 25, and therefore their current is going to be 1.25 like the first one. Then you can calculate what is really the total current, which is 1.25 plus 1.25 plus 208, and that is going to give you the voltmeter reading as I total times R45, because if you go here, you are going to find that the voltmeter is across the 45, then it's going to be whatever current it is going through it times its value. Therefore, we were able to calculate the voltmeter reading as 4.58, which is the total current times the 45, which is going to be 206. Also, we know that the 35, it's the same loop, it has the same current going through, and therefore its value times the current is going to give you the voltage across it, which is 160. If I add all the voltages, this is going to be 398 volts. Then you're going to add the 32 point something here, 31.25, plus the 206 plus the 160. This one is a little bit different, where we have you were gonna show you here, even if like that we have this arrangement by switching on and off, we are going to change the what is really the circuit is looking like. This circuit here, we have EMF equals 36, we have R1 4 ohms, we have R2 equals 6 ohms, and R3 equals 3 ohms. And then we are trying to find what is really the potential difference VAB between the 2 points here when the switch is closed and when the switch is open. And for each resistor, calculate the current through the resistor with S open and S closed. And for each resistor, does the current increase or decrease when switch S is closed? Now the first one is, I'm gonna assume that this one is open, therefore this branch is not gonna be part of the circuit, and then the circuit is gonna be just this here, and that resistor. Then R2 and R3, now they are going to be in series, and therefore VAB is going to be the value of R2 divided by the total resistance, which is R2 plus R3 times EMF. Then it's going to be 6, its value, divided by 9, which is 6 plus 3. Therefore, VAB is 24. Now, when the switch is closed, we are going to have this setting. Then this is 4, this is 6, and this is 3, and this is the EMF. I need to find first what is really the equivalent resistance of 4 and 6, and therefore is going to be 1 over R46 equals 1 over R4 plus 1 over R6, and I have calculated their equivalent resistance to be 2.4. Then now I can replace these two resistors by 2.4, and then I will add to it 3 ohms resistor, so that it will be the total 5.40. In order now to calculate VAB, again I'm gonna say R46, which is the 2.4, divided by the total, which is 5.4 times 36, and that is gonna give me 16 volts. Here I am trying to calculate the current when the switch is open. Then this is my circuit. It is 36 divided by 9, because here I have 2 resistors in series. Then it's gonna be R2 plus R3. They are going to be the 6 plus 3, which is 9. And then the current is gonna be 4. And of course I4, the current that is gonna go through resistor 4 is going to be 0, because the switch is open. And therefore I6 and I3 equals 4 amperes. When the switch is closed, I4 is gonna be VAB, which is 16. We calculate that voltage divided by 4, then it's gonna be 4 amperes. And then also for the 6 ohms is going to be 16 divided by 6, which is 2.67. For I3 here, which is going to go through the resistor, R is going to be R4 plus R6, which is going to be 4 plus 2.67, and that is going to be 6.67. We can see here that I4 increased from 0 to 4, I6 decreased from 4 to 2.6 amperes, and I3 increased from 4 amperes to 6.6 amperes. I'm gonna stop here and have another video.